Thank you for deciding to spending your time for my presentation. This presentation is about geometric interpretations for surfaces using technology, advised by Dr. Cheng, and I'm Lynn. We will introduce the surface. And what's a surface? Here's the definition of a surface. A CK coordinate patch or simple surface is one-to-one CK function. X is defined U to RQ for some k is greater or equal to 1, where U is an open subset of R2 with coordinate U1 and U2. And you can find coordinate patch by dx du1 cross multiply dx du2, and that's not going to be equal to 0 on u. dx du1 represent partial derivative by u1. Here are some examples of surface. So the first one is a sphere, and that's a surface. And second is a torus, that's also surface. And third is the Mungay patch, that's also surface. If you calculated the previous definition, take the partial derivative of u1 and u2 or u and v and cross multiply those results, then they are not going to be equal to 0. In this slide, we're going to talk about the coordinate transformation. So coordinate transformation is x is defined u to r cubed and y is defined v to r cubed, and they are coordinate patches or simple surface. Then we can find y inverse of composition x if u and v has an intersection between that. And we say that's going to be coordinate, CK coordinate transformation. In other words, if u and v does not have any intersections, then coordinate transformation cannot happen. In this slide, we're going to talk about first and second fundamental forms. First fundamental form is the following, that Roman numerical I is equal to Gij, U1, U2, and inner product Xi and Xj. Inner product is just ordinary dot product, and Xi refers partial derivative by Ui. Or this can be also written as 2 by 2 matrix G11 to G22. G11 can be found as X1 dot product X1. And second fundamental form, we can write second fundamental form as the following, Roman numerical 2xy and inner product lxy, and that's going to be equal to sigma ij l ij xy. Or this can be also written as 2 by 2 matrix L11 to L22. We'll see more detail how to calculate first and second fundamental forms in next examples. Here is how we can calculate first and second fundamental form. We're going to use Mungay patch x uv is equal to uv u squared minus 2v squared. To calculate first fundamental form, we need to find partial derivative of u and partial derivative of v. That is, partial derivative of u will going to be x1, that's 1, 0 to u, and partial derivative of v is x2, 0, 1, minus 4v. Remember, if we have a 2 or more variable and take the partial derivative of the others, then we consider the other variable to be constant. And after we got x1 and x2, we can directly calculate dot product. x1 dot product x1 is 1 times 1 is 1, 0 times 0 is 0, 2u times 2u is 4u squared, so we have 1 plus 4u squared. x1 times x2 is the same as x2 dot product x1. 1 times 0 is 0, 0 times 1 is 0, 2u times minus 4v is minus 8uv. x2 dot product x2 is 0 times 0 is 0, 1 times 1 is 1, minus 4v times minus 4v is 16v squared. So we have 1 plus 16v squared. And we can write these informations into the 2 by 2 matrix as the following. Gij is equal to 1 plus 4u squared minus 8uv minus 8uv 1 plus 16v squared. That's how we found first fundamental form. And now we wanted to calculate second fundamental form. We need to have more information for second fundamental form. So first we need to find the n. N is a normal vector to coordinate patch or simple surface in M, and you can calculate this by x1 cross multiply x2 over normal x1 cross multiply x2. And remember from the previous definition, we say it is a coordinate patch if x1 cross multiply x2 is not equal to 0. And see here, minus 2u, 4v, and 1 is certainly not equal to 0. That's why this Monge patch is a surface. And we need to find the second partial derivative. x11 is 0, 0, 2. x12 is going to be second partial derivative by v. So we have one derivative is 0, 0 is 0, to u, because we considered u as a constant, so it's going to be the 0. And that's going to be same for x21. And x22 is going to be 0, 0 minus 4. And we can calculate that Lij equals xij dot product n. L11 is equal to 2 over square root 1 plus 4u squared plus 16v squared. L12 is equal to 0. That's going to be equal to L21. L22 is equal to be minus 4 over square root 1 plus 4u squared plus 16v squared. So we can write this second fundamental form as the following matrix on the left to bottom, blue box. We have Lij is equal to 2 over square root 1 plus 4u squared plus 16v squared, 0, 0, minus 4 over square root 1 plus 4u squared plus 16v squared. So we calculated first and second fundamental form from the previous slide, and we're going to introduce Christoffel symbol for this slide. The Christoffel symbols are the function that is defined on U by Christoph ijk is equal to sigma I is equal to 1 inner product xij xl times g to the lk, and ijk are between 1 and 2. And this symbol can be calculated by Gauss's formula. Xij is equal to Lijn plus sigma k Christoph ij x sub k. Remember that xij was second partial derivatives, and Lij was from the second fundamental form, and we already know what's n, and we just need to figure out what's the Christoffel symbol. In this slide, we're going to talk about geodesic and parallel vector fields, and here's the definition. A unit speed curve gamma s in M is geodesic if and only if triple product of nt and t prime is equivalent to 0. That 3 ball means equivalent, and triple product, you need to do one dot product and one cross product, and order does not matter. Let M be a surface of revolution generated by unit speed curve RT and GT, then every meridian is geodesic, and a circle of latitude is a geodesic if and only if the tangent x1 to the meridians is parallel to the axis of revolution at all points on the circle of latitude. So we'll move on to next slide because I brought the picture that makes you understand better what's geodesic and what is happening with the parallel vector if it's geodesic or non-geodesic, and what is the meridian and the latitude. Before we move on parallel vector, we wanted to see what's meridian and latitude. The meridian looks like that vertical circle on sphere and torus. And we already said that's going to be geodesic. Every meridian is geodesic if it's surface of revolution. Remember that sphere is surface of revolution and torus is also surface of revolution. We learned about this from the cartoon. And the latitude is the horizontal circle with the pink line, and we wanted to see what's the relationship between the geodesics. And here, this is what's happening. So we have two different latitude. One is in the left one is in the latitude on gray circle, and we can see that vector is parallel. The other one on the right side is the latitude, but it is not on the gray circle. It is around somewhere around the degree of pi over 3. That's around the 60 degree. And we can see the vectors are pointing out everywhere, and it is certainly not parallel. So if we have geodesic, then the vectors are going to be the parallel. And if we have non-geodesic, then the vectors are not going to be in the parallel. We're going to talk about mean and Gaussian curvature. So the Gaussian curvature of a surface M at P in M is defined to be Kp is the determinant of Lp. And the mean curvature of a surface M at P in M is defined to be Hp, 1/2 trace of Lp. We care about mean and Gaussian curvature because it's kind of a measurement or tools to measure how much your surface curved. That's why we care about mean and Gaussian curvature. So let's move on for the example. So now we're going to use the same example from the previous slide. That's Monge Pet's xuv is equal to uv u squared minus 2v squared. If you remember from the previous slide, then you can remember that Gaussian curvature can be calculated with the determinant of Lp, and that L looks like somewhat similar from what we saw before, and that L is from the second fundamental form. So at this point, you may just forget about what was the result of Lij. So here's the Lij, what looks like 2 over square root 1 plus 4u squared plus 16b squared, 0, 0, and minus 4 over square root 1 plus 4u squared plus 16b squared. And we can simply get the determinant of Lp by multiplying those two diagonal numbers. So the Gaussian curvature, we're going to be turns out 2 times minus 4 is minus 8, and 1 plus over 1 plus 4u squared plus 16v squared. And mean curvature, you can calculate this by 1/2 of adding those two numbers, and that's going to be 2 minus 4 is minus 2, and minus 2 and 2 canceled out, so we are left with minus 1 over square root 1 plus 4u squared plus 16v squared. And we can check that Gaussian and mean curvature is curved negatively, so that means even if our given statement or equation looks like the positive, the Gaussian and mean curvature actually turns out to be the negative, which is quite interesting. So that was all about my presentation. Thanks again to spend your time with my presentation, and hope you understand better with what's happening with the surfaces and get at least the idea about what is the simple surface. And thanks again. And this slide is for my references. Thank you.